All right. We are sticking again with kind of fixed axis rotation. Meaning that the rotation axis, while it might be allowed to move, and if we do allow it to move, we'll probably put it at the center of mass of the system. Or more likely than not, we're going to try to keep it perfectly stationary, and it's always going to be pointing in the same direction. And again, if we think of the rotation axis as telling us kind of what the thing is rotating around, what that means is, or if you think of a rotating object, right, that's always rotating kind of in the same plane versus, doing this or this or this. It might be the case that we allow things to speed up or slow down as they rotate, but they'll still always be rotating kind of in the same direction. So you have some fixed angular velocity vector, omega, that corresponds to that information. Without loss of generality, kind of log, as the mathematicians might say, let's put the axis of rotation along the z-axis. You're allowed to put your coordinate system in any way you want. Let's put it along the z-axis. Under these kind of assumptions, it's nice that, for example, if I have some extended system here, which I've kind of sketched out as this kind of blue blob, and there's a particular part of this blob, or it's an individual particle itself, I'll just say dm, but it could be that it's not an extended system, but there's just a single particle that's rotating around this particular rotation axis. The position vector from the origin, wherever the origin is, which let's make it more explicit, that doesn't necessarily even have to be in the object, right? If this goes down here, or the rotation axis, I could have the origin say here, in which case the position vector, the 3D position vector, might look something like that as it points to the object. But I've put the origin along the axis of rotation in this case. The nice thing about that is that for any particle in the system, under these assumptions, its kind of polar coordinate radius is fixed. All particles in this case have a fixed polar radius. I'll use capital R. And based on this drawing, the polar radius, let's see if red comes out, might be kind of the distance that goes from the axis of rotation to the particle, but has no z component. So where if r, regular position vector r, might have some coordinate, kind of x comma y comma z, the polar coordinate position vector, right, might in this case just be x comma y comma 0, right? The part that points from the rotation axis to the location of the particle. And this big R, which in this case is just kind of x squared plus y squared all into the square root, is fixed in this case. Which is kind of nice. Because if you think of in polar coordinates, well, actually we can upgrade this to polar coordinates plus the z direction is what's called cylindrical coordinates. In cylindrical coordinates, which talks about kind of r, theta, z, as kind of the three axes. So same thing as polar coordinates, but then you add kind of in and out of the page, if you're thinking 2D, a z direction, which ends up being the same exact thing as the Cartesian z direction. In polar coordinates, the velocity vector then is something like, first I need what's going on in the radial direction. Well, it's not getting closer or farther away from the origin. In the tangential direction, it looks something like this, and then it's not moving kind of up or down as well. So in this case, the velocity vector is pretty simple, right? The velocity vector then looks like it's going to be 0. I might call that omega for theta dot if I want to use that symbol, such that the magnitude of this rigid body rotation is this r times omega, which might look familiar. I think typically it's this kind of rotational analogs. When you have something that isn't free to move arbitrarily in all directions, but it's kind of rigid body is one example where it's not getting closer or farther away from the origin, and it's not moving kind of parallel to the origin as well. The velocity then is just r times omega as it rotates around the z-axis. And this, of course, is one specific example of the more general thing we talked about where, again, always remember, in general, the velocity is given by omega across the 3D position. You might try to convince yourself that that also gives you this result in the case of rigid body rotation, where there's no motion in the radial or z direction. But what I ultimately want to do is I want to try to think about what can I say about continuous systems and the resulting angular momentum. Especially if I can draw towards things like angular momentum being conserved. So if we go back up to our drawing and think of how we might try to calculate the angular momentum of a continuous system, well, of course, I can always start with that the total angular momentum of a system is going to be the sum of all the individual angular momentums of all the particles within the system. But now, again, let's make this, how does this translate to something that's continuous? So this is just m sub I, r sub I cross v sub I. And again, let me kind of just draw, and maybe I have some arbitrary thing, which in itself might have kind of some 3D shape. It doesn't have to be a pancake or anything like that, but there's some 3D shape to it as it rotates around some rotation axis, which again I will always align with z. As it does this, so that there could be, say, some particle here, right, some dm, which has a well-defined position. It might have a well-defined velocity, which particularly if it's rigid body, there are some relationships between those two. What does the angular momentum become for a continuous system like this? Well, again, if you think of that particular particle I drew, right, and think of dividing it up more and more and more, the amount of mass is shrinking, though its position and velocities are not. It's not that its velocity is getting smaller as you zoom in and more, or that its positions are getting smaller as you zoom in more and more. But its mass is getting smaller. So then this becomes not a sum, but an integral of kind of r cross v, and then you're integrating over all the little mass bits. Each of them has their own r and v, so all of this is changing for a continuous system. And you integrate over all the mass, that's the angular momentum. Let's see if we can't simplify this in the case of rigid body rotation and see what we get. So again, this is the integral of r cross v, all integrate over dm. V, however, for these rigid bodies, right, we can write generally as this integral of r cross, and then this is omega cross r, all integrate over dm. But then I can use one of those handy triple product rules. In this case, I believe it's the back cab rule that you can use. And so this becomes, once you look that up, r cross r dot r multiplied by omega minus then r dot omega multiplied by r. All this is over, again, dm. So that's just a vector identity. Some of these can simplify. So this becomes an integral, a vector dotted with itself. It's just the magnitude squared, all multiplied by vector omega. And then it doesn't look like I can yet say anything about this dot product times r all over dm. Now we can generalize this a little, or sorry, we can make this more specific to this case where omega in Cartesian coordinates only has a z component, right? Because we're putting the z direction along the axis of rotation, and that's where omega is. So I can use that along with still a very general position vector that has some coordinates x, y, and z, and write this now as this integral. Let me skip a line. This integral, let's see, the position squared, looks like it's going to be x squared plus y squared plus z squared, all times omega. Well, maybe I'll just leave it as a vector. And then r dot omega means I take the x components, multiply them together, add that to the y components after I multiply them together, and then add to it the z components after I multiply them together, which is going to be the only thing that doesn't have a zero. So then it looks like it's just omega times z, again multiplied by the vector r. And then since omega only has a z component, right, this first part here really only has a z component, where this has an x, a y, and a z component. So then at the end of the day, this looks like it's an integral over, and then what's the vector that ultimately is left over at the end of the day? Right, there's no z component for that thing that's multiplied by omega, but then it looks like it's going to be negative omega z times x in the x direction. It's going to be negative omega z times y in the y direction. Then it looks like it's going to be x squared plus y squared plus z squared all times omega, and then you're going to subtract omega times z times the z component of r, which is again z. So it looks like you then have a minus omega z squared. So then this looks like it's x squared plus y squared all multiplied by omega in the z direction. And that's integrated over dm. And that particularly is the angular momentum of this kind of big rigid object. There's a component that looks different in the z direction, the part that's kind of aligned with the rotation axis. And then there are these cross terms that do not, that are pointing the x and the y direction, which is not where the rotation is the motion is happening there, but the rotation is not happening there, corresponding to omega. So this is kind of a general expression for how you would evaluate the angular momentum of an object undergoing rigid body rotation. It would have three components. So this also shows that omega and the angular momentum are not necessarily always parallel to one another. Omega is pointing along the z direction, but notice here that it looks like the angular momentum L has an x, a y, and a z component, assuming that the integral doesn't make those result as zero. So it is not generally true, as your intro sequence might have insinuated, it is not generally true that the angular momentum vector is always parallel to the rotational axis or the omega vector, the angular velocity. That is not a generally true statement. Though it is often very helpful to think of the angular momentum vector as also kind of signifying rotation, where if L is pointing up, there's rotation that's going on around that direction. But that's not generally the case, unless you make specific assumptions. We've already made the case that the origin is stationary, that the thing is rigid, And so now we're simply going to focus on the z component, L sub z specifically. Assuming that, or really just we're focusing on how that particular component of the angular momentum can or cannot change, right, while holding the axis of rotation constant. The nice thing is that when we do this, we're getting away from kind of the vector notation of it all, because then this says that just the z component of L is this integral of x squared plus y squared dm, all multiplied by omega, where omega, I assumed, is a constant, at least a constant relative to m, right? It's the same omega for every piece of mass in the system, so I can take it out. Omega might change with time, but that means I can still take it out of an integral that's over mass. This here is what's called the rotational inertia. Usually given capital letter I. More technically, I should be saying I sub z as the rotational inertia of the system, which allows you to write this component of the angular momentum as just I times omega. Here is a thing that looks more analogous to regular momentum. Regular momentum, we said, is this thing called mass times this thing called velocity. Here now we're able to say for rigid body rotation, we can talk about the z component of the angular momentum as being this thing, not mass, but called rotational inertia, times not velocity, but multiplied by angular velocity. Where the role of mass is now being played by something that does involve mass. It's an integral over dm, but it's kind of a mass, it involves positions as well. Omega then, of course, being the angular velocity. And by focusing on just this component here that is parallel, anti-parallel to the rotation axis, here notice then that, right, if we want to think of this as a vector, right, the z component really is I times omega, where it is parallel to the rotation axis in this case. But really what we're doing is we're constraining ourselves to just look at a particular component of the angular momentum. And sometimes it is often the case, or sometimes it is the case, that the other components of the angular momentum are zero. So that this really is true in the 3D sense rather than just focusing on z for a more general angular momentum vector. So this is where the second half of the textbook gets into it, where the more general problem without all these assumptions I'm making, rather than talking about the rotational inertia as a number, like what I've written down here, it actually ends up being something called a tensor. It ends up being, for a three-dimensional problem, it ends up being a 3x3 matrix of 9 numbers. Not all independent from one another. There are some relationships, but essentially you have to write down 9 numbers that gives you the rotational inertias as you try to rotate objects around a more general rotation axis compared to us kind of just holding it fixed here and assuming that there's some sort of geometric constraints that's holding it so that the rotation axis is always pointing in the same direction. Though again, under our assumptions, the nice thing is that we can stop really thinking about this as vectors, which will make our life a little bit easier. And we're going to see that essentially, again, right, mass is going to rotational inertia. Velocity is going to angular velocity, such that P, which is mv, then L, or I guess capital L in this case, is I omega. And we haven't done energy yet, but when we do things like energy, where we're going to write that kinetic energy is 1/2 mv squared, we can still say that the kinetic energy when you are dealing with rotation, turns out you can write down as 1/2 I omega squared. So these will be very helpful, useful analogies or connections between them. Though in this case now, there is the more challenging problem of if I want to talk about the angular momentum of a solid system, or point particles, for a fixed rotation axis, I have to be able to evaluate this rotational inertia first. So the rest of this lecture, I think, is just going to be doing a bunch of problems or examples of this. And these are things you'll see, like these are things that typically it was a handout or it's a table in one of your books, right? The rotational inertia of a sphere, the rotational inertia of a shell or a ring or a hoop. We actually now have the sophistication where we can actually calculate these things. If I've given that and I know omega, that tells me the angular momentum. And then based on what we talked about in the last lecture, I can say things about whether or not the angular momentum is conserved or not. So let's take as a simple example 2 point particles of mass little m, and they're connected to a thin but massless rod that has length r. And I'm rotating this around the object's center of mass, which is going to be obviously halfway in between the two particles. Oh, I guess let me make one point actually before we go into the example. What is this x squared plus y squared in this case? If I want to think of this again, if things are rotating, polar coordinates are probably going to be the thing you find most relevant to use in these sorts of systems. But scrolling up, x squared plus y squared, that's really just the polar radius, capital R. So I could also write, let's see, where can I write this? I could also write I omega as where I is the integral of polar coordinate r squared over dm. Where r in this case is, right, again, you can think of it as the polar coordinate r. But you can also think of it as the distance from the axis of rotation. Right? If the rotation axis is an infinite line, right, and I have a point here, the distance from the axis of rotation, right, you imagine, which part of the axis do I use, right? The part that's kind of perpendicular out from the axis of rotation to that point would then be, which again, as it rotates, that is the same thing as the polar radius. So you can think of also as the distance from the axis of rotation. All right. So in this case, what is the rotational inertia of two point particles? Well, we've written down that it's the polar radius r times dm. We could go the other way. Again, what is this if this weren't a bunch of continuous particles, but then this would just be r squared times m, right, for the individual particles that make up the system. So then it looks like I find the distance from the axis of rotation, I square it, I multiply by the mass, and that's the inertia component for that mass element. So in this case, it just looks like it's going to be m r squared plus m r squared, or 2m r squared for the rotational inertia of this kind of massless baton with two balls at the end. Let's do it again. But now let's make the rod actually have some mass. Maybe it's two balls that have mass m, but then a uniform rod that has overall mass capital M. Since it's uniform, that then means it will have a uniform mass density. So this is now the kind of massive rod. Well, in this case, the total rotational inertia is going to be the sum of the rotational inertias of the objects that make up the problem. And a key, of course, is that they're all rotating around the same axis of rotation that I've placed, again, at the center of mass. Again, those are choices I'm making, but it turns out it will simplify your life a lot. And we'll see that also in the next video when we do the parallel axis theorem. So in this case, since they all have the same rotation axis, that's rotating, that gives you some omega value that's the same for everyone. You can think of this as the rotational inertia is the sum of the inertias, which then looks like it's going to be I of the rod plus the rotational inertia of the two balls, which we already said was 2m r squared, 2 little m r squared. So now I just got to figure out the rotational inertia of the rod. So I rod is then going to be the integral of, now the distance from the axis of rotation, maybe I shouldn't have used capital R for the distance to the two masses, because really this is, if we go back to our general definition, right, the positions of all these individual mass elements are changing, right? So I can't just plug in capital R squared, this capital R squared in right away. But really, this is an integral over, in this case, really it's an integral over x. Right? You can think of this as x squared times dm, because all the mass lies along the x-axis. If I want to make the x-axis horizontal, where I could draw my position out to some x value, and there's some little dm located there. I'm going to add up all of the dm's that each have their own unique position. The position itself may not be small. So if it's a uniform mass distribution, of course, it's 1d, so that means this is dm over dx. Again, it's 1d, everything's along the x direction. So then it looks like this becomes the integral of x squared sigma naught times dx. Now I've turned this into an integral over a bunch of x's. I'm going from negative r to capital R, or positive r rather. And it looks like this is then going to be 2r cubed sigma naught over 3 at the end of the day. Now again, dimensionally, it would be nice, just looking up here, where rotational inertia looks like it's a position squared times a mass. So can I write this rather as maybe the total mass of the rod times a position squared? Well, in that case, I need to know what the total mass of the rod is, which then is just integral sigma over dx, which essentially just comes from that. So since this is a constant, right, I'm going from negative r to positive r, it looks like this is then just 2 sigma naught times r as the total mass of the system. So in this case, I can factor out an r squared over 3, then the thing that's left over is 2 sigma naught times r, which is just the mass. So then it looks like this is then the total mass, r squared divided by 3, is the mass of the rod. And overall, at the end of the day, I total looks like it's going to be 2 little m r squared plus 1/3 mass of the rod, r squared. Again, the units, of course, have to make sense. Else, what are we doing? Let's take one of those ones that you remember kind of having to look up in your textbook during intro physics. Let's do a ring with uniform mass, or uniform mass density. It has a total mass, capital M, and radius, capital R. What is the rotational inertia of this ring? And again, it's rotating around some axis, which I will place at the center of mass for this ring. All right. The rotational inertia then is an integral over the position of all these mass elements are from the center of mass. So I can even kind of draw it out, kind of draws out to some little dm that's located there. But since this is a ring, the nice thing is that every part of the ring is a distance r squared away from the center of mass. So that's actually a constant times dm. And again, to emphasize that it's a constant, I'll take it out of the integral. Since every mass element is the same distance away from the center. So in the integral of mass, that just looks like this is then just capital M r squared, which is indeed what you would get when you look it up in a book for a ring. But as a nice way to review integrals and polar coordinates, let's also reach this conclusion using the mass density as well. If I was just told there was a uniform mass density and I wanted to write the rotational inertia in terms of sigma and r squared, perhaps, or sigma and r, how might I do that? Well, again, if it's a 1D mass density, then that means dm over d, right, some 1D arc length. This really is a 1D problem because mass is kind of only distributed in a 1D ring around, and that's some constant sigma. If we take a bird's eye view to the ring, right, and here's my little dm, I ultimately want to integrate over all these little dm components, which are broken up into all these little segments, where a particular segment might be located, right, with some theta value, and then it changes to some different segment that has some kind of delta theta as it moves along. So that just seems like it's arc, right? It's arc length of a circle. We know that if we go 2 pi radians around, then we get the full circumference of the circle, 2 pi times r. But what is the length of just an arc if you only move an angle theta, not full 2 pi radians, but only an angle theta? This arc length then is what? It's just, it turns out, just d theta times r. And again, when d theta goes from 0 to 2 pi, this becomes 2 pi r, the full circumference of the circle, which makes sense. So in this case, the dm, a little bit of mass, is contained in sigma times r times d theta in this case. So the rotational inertia, which again is r squared integral over m, then is going to be r squared, the integral over sigma r d theta, sigma naught, and we go from 0 to 2 pi along the entire thing. So then this looks like it's then just 2 pi r cubed times sigma naught would be the rotational inertia of this ring. And do we, of course, get that this is the same thing as m times r squared? Sure. Because I could go back here and write that I could write that the mass then is the integral of 0 to 2 pi of sigma naught times r d theta, or that the total mass is 2 pi sigma naught times r. And then, of course, notice that this looks like it's then 2 pi sigma naught times r. If I factor out an r squared, that thing in parentheses then, of course, is just m times r squared. All right, not too bad. Let's do one more. Let's not do a thin ring. Let's do a thin shell. All right, so a kind of 3D spherical shell of radius r. And I'll put the origin at the center of mass. So every little mass element, right, there's some general position vector r that reaches out to the shell. It's a hollow shell that has some little dm over it. And it has a uniform mass density. Now, how do we do this? Well, perhaps maybe the easier one to do first is the total mass of the system, m total, which is just going to be the integral over dm, which is then going to be the integral of sigma naught times dA. If this is a 2D mass density, then sigma is dm over dA, a little patch of mass, or a little patch of area rather. So if I draw it, again, if I think of this as a sphere, right, there's a little patch that's drawn out, over some small location on the surface of the sphere. That's dA. Now, doing this in Cartesian coordinates would be a nightmare. Doing this in cylindrical coordinates would be a nightmare. Doing this in spherical polar coordinates, that makes more sense. Because in this case, let's remind ourselves what is spherical polar coordinates. So if I have my Cartesian axes, I have some location of some position here, which is r, I could imagine kind of projecting the shadow of this vector into the xy plane. So here's kind of the shadow of that vector in the xy plane. And what are my three coordinates? There's some radius r, which I'll use little r instead of capital R, which I'm reserving for polar coordinates. There's some radius r, that's one of my coordinates. How far away am I from the origin? There's this angle here, which is the azimuthal angle theta, or sorry, phi. Phi kind of giving you how much you have to swing around relative to the x-axis. And then there's the altitude coordinate theta, which tells you how far away you are from the z-axis. And you have to be careful because different books and different websites use different conventions. I have seen cases where phi and theta are switched in terms of which symbol stands for which. So you have to be careful in that case. Where r is always assumed to be greater than 0 or equal to 0. Phi, in this case, ranges between 0 and 2 pi, right? So you can go all the way around. But so to not double count, theta only ranges from 0 to pi. And in those restrictions, I can uniquely define every point in this 3D space by a value of r, phi, and theta. So again, this is, or at least I know it as the altitude, the azimuthal angle, and then of course the radius has a funky r. The radius. If I want to do now integrals, writing these down as vectors, we did the cylindrical version of writing these down as vectors and taking derivatives. You could do the same thing, of course, with spherical coordinates. It's a bit of a mess, and I don't think we'll actually need it for anything. So let's not worry about writing these, vectors within this coordinate system. Though if we want to do integrals, of course, we need to know kind of what are the 2D and 3D elements with spherical polar coordinates. And so again, kind of the way you do it is you imagine putting yourself out to some location, some fixed location. And then if I want to find a length element, I imagine changing my direction by a little bit in whatever dimension I'm moving in. In this case, if I went a little bit farther from the origin, a little bit towards the origin, my length element dl would just be dr in this case. But I could ask myself now with the shell, how can I get an area element where I move a little bit And since we're on a shell, notice that the radius is not changing anywhere on the shell. We're the same distance from the origin. The spherical radius is the same for every point on the shell. So on the shell, if I want to get what's a little bit of area, ultimately I'm moving a little bit in kind of the phi direction, and then I'm moving a little bit in the theta direction as well. I said those backwards. Right? This part would correspond to a little bit of change in theta. This part here would correspond to a change in phi. And then that kind of drags out a little square, or a little kind of arced square on the surface of the shell. And if I can compute the area of that little slab, that gives me dA. Right? Whatever this is dA. Let me zoom in, kind of expand out what that arc kind of looked like. Where kind of one direction is kind of changing in phi, we'll call that the red section, and then the black section is kind of changing in theta. And whatever this is, that's then what my dA is. So the area of a rectangle is length times width. So all I have to do is figure out what is the length of one of these black arcs and the length of one of these red arcs, multiply them together, and I'm done. And of course, this has to be an area. So I can't just say d phi times d theta, because the units are wrong. It doesn't make sense. The units have to make up. I better have units of area, meters squared, at the end of the day. And of course, what comes to help us is this idea of arc here. For one-dimensional arc, right, essentially what each of these sides of this little curved rectangle is, I'm sweeping out a little bit of arc in each direction. So to me, this suggests that if I'm keeping everything else fixed and moving only in theta at a radius r, then this is r times d theta, is kind of the length of one of those black arcs. Now the red ones, admittedly, it's a little bit more subtle because this takes a little bit of visualization, right? If I have a very, very small value for the altitude theta, and I'm just kind of a little bit off from the rotation axis, right? Rotating, right, as I sweep around, I'm sweeping around, the tip of my pencil is sweeping a much smaller circle in this case. Compared to if I have a large altitude, this is sweeping out a much bigger circle as I move around. So I imagine that a little bit of arc, right? So instead of doing a full circle, if I just do a little arc in this case, the size of the arc I sweep out here is different than the size of the arc I sweep out here for the same kind of delta phi. So I imagine that the value of theta is also going to play a role. And I'll leave it to you can look at your calculus book to see kind of what this is. Essentially, it's not r that matters, but it's r sine of theta that matters. And that's all multiplied by d phi. So at the end of the day, dA looks like it's going to be r squared sine of theta, d theta, d phi. The volume element, I guess just for completion, again, you ask yourself kind of how much, instead of doing the area of a slab, essentially you would have that same kind of slab, but then you would move out in radius, in that spot too, and ask what's the volume of this kind of rectangular thing. In that case, it's just the same thing, but there's a dr thrown in as well, d theta, d phi. Again, the units make sense. I have the r squared, and then I have the dr. Both of those have units of, or capital R and little r have units of position. So that ultimately is units of position cubed, or volume. So then the total mass looks like it's an integral over dm, which then is going to be an integral of sigma times dA. Now you could realize that sigma is a constant, so this is really just the integral of sigma over dA. And what's the area of a shell? Well, this better be 4 pi times r squared. Of course, we could always convince ourselves of that. When what is dA? It looks like it's going to be r squared sine of theta d phi. So this actually becomes a double integral. First integral from 0 to pi, because that's for theta, and then this goes from 0 to 2 pi. And I'll let you fill in the blanks that indeed you get 4 pi r squared times sigma at the end of the day. Again, perhaps not too surprising, but it's always nice when different approaches give you the same answer, especially when they're kind of required to for sanity reasons. Let's see, where can I? I would like to not move to a new page. Oops. So now with the total mass calculated, now we need to calculate the rotational inertia. And why this is tricky is because the rotational inertia, I, has an integral of, again, I shouldn't have been using capital R in this case, but let me write r kind of perpendicular squared times dm, where this r perpendicular is the distance of a mass element from the rotation axis, which is different. It's not like the ring where they were all the same distance from the rotation axis, but for a shell, it is different. For example, up here on top, right, there's kind of a ring here where they're all pretty close to the rotation axis, compared to here where there's a lot of distance between the rotation axis and all the little dm's that are located there. And then it gets small again, down here. So for a given value of theta as you go down the shell, that loop that gets drawn out for a given value of theta changes. And so what is that relationship? Well, it's not too bad, because I could take kind of a cross section. You can imagine kind of slicing the shell in half. So then you just have a circle here. And the corresponding, this right here then is r perpendicular, again, if this is the z-axis. But then this position here is r. And it has moved and is located at some angle theta from z, right, whatever that altitude is. And thankfully, it looks like there is a right triangle here. That r, in this case, looks like it's just, I guess, the hypotenuse is r. And it looks like I'm looking at the opposite. So sine of theta is opposite over hypotenuse, or that r times sine theta is this perpendicular distance. That is the distance that the little dm is away from the rotation axis. But this little r is the distance it is from the origin. So that is nice because all mass elements are a distance capital R away from the origin, right? Whatever the radius of the shell is. Maybe I should call it R naught, right? Let's call it R naught here. So going back, let's see, all these are R naught. Oh, sorry, that's not R naught. This is R naught. This actually I might write as little r squared since it's the 3D r. And then, right, for no change in the radius, that's r naught, thin shell of radius r naught. Then it looks like these are r naughts. R naughts. There we go. Because then this becomes an integral of not we've now figured out r perpendicular. It looks like it's r naught sine of theta all squared multiplied by dm. This ends up then being an integral of r naught squared sine theta squared. And then dm we said is sigma naught times dA, which is r naught squared, another sine of theta, d theta, d phi. This is indeed a double integral, going from 0 to pi for theta and 0 to 2 pi for phi. So this ultimately is an integral over, right, sigma is a constant, r is a constant, sine of theta is not a constant, so this ultimately is an integral over sine cubed. And if I do the integral in the opposite order, the phi component gives you a 2 pi, looks like it's sigma naught to the fourth, or sorry, r naught to the fourth, sigma integral of sine cubed theta d theta, going from 0 to pi. In which case then, right, power reduction formulas, if you look at a list of trig identities, you can turn higher powers of trig functions into products of lower powers of trig functions. Ultimately, at the end of the day, this integral you can evaluate, and again, I'll leave it to you to kind of try it on your own. Ends up becoming 4/3 at the end of the day. And then, since we have an expression for the mass, we can do the same thing as what we did before. You can ultimately derive that this is 2/3 the total mass times r naught squared. Again, a mass times a position squared is the rotational inertia of the system. And if you look it up in a textbook, right, that is exactly what you'll see written down for a hollow shell. But again, it's all the idea that it's the distance from the rotation axis squared times the amount of mass that's at that position. So in this case, we considered a bunch of dm's over a shell. The distance from the rotation axis did change, which is what made this a little bit more complicated than the hoop. But using spherical polar coordinates from Calc 3 or whenever you learn that, we could piece it together and actually derive things like that the rotational inertia of a thin shell is 2/3 m times r naught squared. All right, you can try a couple more shapes on your own.